Welcome back to Lecture 2 in the Introduction to Electromagnetism series here in this channel. This lecture will be going over superposition and electric fields. So superposition, what happens if there are more than two charges? So last lecture we went over a couple of cases where we had two charges and we looked at the forces on those charges and the direction of the force on those charges due to the Coulomb force. But what about if there are more than two charges? Well, in this case, we use the principle of superposition. So for example, in this case, we have four charges, Q1, Q2, Q3, and Q4, and the principle of superposition states that the force on a given particle is equal to the sum of the forces present due to all the particles present. So mathematically, this is a sum of vectors. So the force, for example, on particle 1 here is going to be equal to the vector of the force by particle 2 on particle 1 plus the force by particle 3 on particle 1 plus the force by particle 4 on particle 1. And then writing this very compactly, this is just a sum of these force vectors over all the other particles onto particle 1. And then this force vector is just given by Coulomb's law, 1 over 4 pi epsilon naught q1 times qi, whatever particle we're looking at the case, the distance between these two particles squared, and then the appropriate unit vector. So perhaps that may have been a little bit confusing. Maybe the math wasn't very clear. So let's do an example. So in this case, if each charge is the same magnitude, and if each charge is equidistant from each other, so the same distance away from each other, what direction is the force pointing on charge Q1? So here is charge Q1. It's going to be feeling a force both from charge Q2 and charge Q3. So let's take this step by step. So first, looking at charge Q2, we know that like charges repel. So charge Q2, the force on charge Q1, charge Q1 is going to want to move away from charge Q2. So the force vector is going to be in roughly this direction, pointing away from charge Q2. Now looking at charge Q3, we know that opposite charges attract. So charge Q1 is going to be pulled towards charge Q3. So the vector is going to look something like this. And it's going to be roughly the same magnitude as F21, as the charges are the same magnitude and the charges are equidistant away from each other. So now, how do we find the total force on charge Q1? Well, we just add up these vectors and we get the total force acting on charge Q1, F1, and it will be roughly in this direction if we add these two vectors. If you have forgotten how to add vectors, you simply add them tail to head in consecutive order. It does not matter the order. So we have F31 pointing here. On the head of F31, we add the tail of F21, and it points in this direction, and then the resulting difference between the starting point and the ending point of these two vectors is the F1 vector, our total force. So we can continue with this example and make things a little bit more mathematical. So we can say that each charge has a magnitude of 1 coulomb. So we have plus 1 coulomb, and then minus 1 coulomb charge. And we can say that these charges are still equidistant from each other, making an equilateral triangle, and that the distance is 2 meters. And then we can ask more specifically, what is the magnitude of this force on Q1? We'll be adding vectors in this problem, so it's useful to create our own coordinate system. So we've made x pointing in the horizontal direction and y pointing in the vertical direction. And we can again start with F21. So what is the force by Q2 onto Q1? From Coulomb's law, we know that this is given by the equation 1 over 4 pi epsilon naught Q1 Q2 divided by the distance between the two particles squared, and then multiplied by the unit vector pointing from Q2 to Q1. So R21, the unit vector, is given here, pointing from Q2 to Q1. And then we know the value of both Q1 and Q2 is 1 coulomb, and the distance between the two charges is 2 meters. So we have 2 squared on the bottom. And this gives a force magnitude of 1 over 16 pi epsilon naught. We can then, instead of writing r hat 21, our unit vector, we can use our coordinate system. So we know that this unit vector, knowing that this is an equilateral triangle and this inner angle will be 60 degrees, we know that in the x direction, the value of this unit vector will be cosine of 60 degrees, and in the y direction, the value of this unit vector will be sine of 60 degrees. Now, we can use a similar process to calculate F31, the force by Q3 on Q1. We again use Coulomb's law, so we have 1 over 4 pi epsilon naught Q1 times Q3 divided by the distance between the two charges squared, and then the unit vector r hat 31. R hat 31 is given here, pointing from Q3 to Q1, and then now we can simply plug in the values. The distance between the two charges is still 2 meters, so we have 2 meters squared on the bottom, but on the top we have Q1 being positive 1 coulomb and Q3 being negative 1 coulomb, which is why we have this negative sign out front. And then still r hat 31, the unit vector. Now, because of this negative sign, when we write out F31, the force by Q3 on Q1, the negative sign flips the direction of the vector around, and now it points from Q1 to Q3. This is what's expected as these charges are opposite in sign, and therefore the force will be attractive. Now, we can again use our coordinate system to replace r hat 31 using sines and cosines. Because this is an equilateral triangle, we know that this angle is still 60 degrees. R31 is pointing in the negative x direction, so we'll have a negative cosine of 60 degrees for the x direction, but it's still pointing in the positive y direction, so we'll have a positive sine of 60 degrees for the y direction. Now, the total force on Q1 is given by the sum of these two vectors, so F31 plus F21. Now, when adding vectors, we add by component, so we add both the x components separately from the y components. So the magnitude out front for both vectors is 1 over 16 pi epsilon naught, so we can again bring that out front when adding these two vectors. For the x component, we have a negative sign canceling out with a negative sign for F31, giving us a positive cosine of 60 degrees, and for F21, again, in the x direction, we have positive cosine of 60 degrees. So that gives us 2 cosine of 60 degrees in the x direction. For the y direction, we have negative sine of 60 degrees for F31 and positive sine of 60 degrees for F21. What this means is that when we add these two components, we end up with 0 as they exactly cancel each other out. Therefore, when we write this out, taking advantage of the fact that cosine of 60 degrees is simply 1/2, we end up with a vector that has a magnitude of 1 over 16 pi epsilon naught pointing in the x hat direction. When we draw this vector, F1, we, just like before, when we predicted it without using all these exact numbers, it points exactly in the x direction and has a magnitude now of 1 over 16 pi epsilon naught. So now we're going to switch gears a little bit and talk about electric field. So electric charge has an associated electric field with it, and the magnitude and direction of this electric field is related to the Coulomb force, as it's actually what provides the Coulomb force. So mathematically, if we want to write it out, we have electric field is going to be given by F naught, which is the Coulombic force on a particle Q naught, divided by the charge of that particle Q naught. Because we're dividing a force, newtons, by a charge, coulombs, the unit of electric field is going to be given by newtons per coulomb. But what do I mean by this charge Q naught and the Coulombic force on this particle charge Q naught? So if I have, say, a particle that has charge Q1, and I ask, what is the electric field here at this arrow due to this charge Q1? What I can do is a little bit of a thought experiment. I can say, okay, where I want to evaluate this electric field, I can put an imaginary charge there. Let's call it Q0. It doesn't matter what the sign of this charge is or what the magnitude of this charge is, but let's just imagine that it's there. What I can then do is calculate the force on this imaginary particle, Q0, and that force is going to be given by Coulomb's law. So F10, the force by Q1 on Q0 is going to be given by Coulomb's law, 1 over 4 pi epsilon naught Q1 Q0 divided by r squared times the unit vector R10, here. And then if I want to calculate the electric field from this, I just use this equation that is given. An electric field is going to be given by this Coulombic force divided by the charge of our imaginary particle, and this gives us an electric field of 1 over 4 pi epsilon naught, the charge of Q1 divided by the distance squared, and then the unit vector r hat 1, 0. And this is the general idea for calculating electric field. We imagine a imaginary charge, Q naught, at some location where we wish to evaluate this electric field. We calculate the Coulomb force at this location on this imaginary charge, and then by dividing by the charge of our imaginary particle, we can then calculate the electric field. So because we can place our imaginary charge Q naught anywhere we would like, the electric field at any point can be calculated due to a single point charge Q1, and this is going to be given by E is equal to 1 over 4 pi epsilon naught Q1 divided by the distance between the 2 points squared multiplied by the unit vector pointing from Q1 to our imaginary charge Q0. Now, just like forces, just like the Coulomb force, the electric field follows the principle of superposition. So if we have more than one charged particle, so not only do we have Q1, but maybe we have Q2 and Q3 as well, we simply add up the vectors of the electric field from each of these contributions, and we get the total electric field. So again, this can be written as a sum of electric field vectors and is given explicitly by this equation here, 1 over 4 pi epsilon naught, the sum of each charge present divided by the distance between each charge and wherever we are evaluating the electric field, and then multiplied by each vector is multiplied by its unit vector pointing from the charge to the point of evaluation. So as an example, a common arrangement of charge is the electric dipole. This is where we have one positive charge and one negative charge separated by a distance d. And if we want to measure along this dipole axis where these two charges line up, if we want to measure our electric field somewhere along this axis, if we are distance r from the dipole center, so the dipole center is here. If we want to measure the electric field at some point, a distance r from this dipole center, the electric field can be shown to be 1 over 4 pi epsilon naught 2 times q, which is the charge of each particle, times d, the distance between the two particles, divided by r to the third. So r is this distance from the dipole center. This can be written more succinctly as 1 over 4 pi epsilon naught 2p over r cubed, where p is equal to qd, and this is the dipole moment. So the dipole moment is the charge of each particle within the dipole multiplied by the distance between the two charges. So thus far, we have only used point charges, so particles of charge that aren't spread over some space. However, charge can be spread over some macroscopic volume or surface, and using a bit of calculus, we can solve these types of problems. So currently our equation for the electric field looks something like this. So the electric field is equal to 1 over 4 pi epsilon naught. And then for multiple charges, we take a sum over the charge of the particle divided by the distance between the particle and wherever we are evaluating the electric field, and then the unit vector pointing from each particle to wherever we are evaluating the electric field. So if we have a continuous charge, we can't use a discrete sum like this. We have to use calculus, so we use a integral instead of a discrete sum. So here we have electric field is equal to 1 over 4 pi epsilon naught, the integral of r hat, the same unit vector, divided by r squared dq. So what do I mean by this dq? Well, suppose that this blue here is some spread charge over some surface. dq is going to be some little bit of charge on that surface. R is the distance between that little bit of charge and wherever we are evaluating the electric field. R hat is the direction of this vector pointing from this little bit of charge to wherever we are evaluating the electric field. And then what we do is for each of these little bits of charges, we slowly integrate over this entire blue surface. And that will eventually give us our resulting electric field vector. A common example of a continuous charge problem is the ring charge. So shown here in blue is a ring of continuous charge with a radius r. And we want to evaluate the electric field along the center axis of this ring, but at some point z above the ring itself. So here is the point that we wish to evaluate the electric field. If we look at some small charge section, dq, and we draw a vector pointing from this dq to the electric field evaluation point, we have a distance of r, and it points from dq to the electric field evaluation point. And this makes an angle theta with the plane of the ring itself. If this charge is positive, which here it's given to be positive, this would result in an electric field pointing away from the charge in this direction. Now we can also evaluate a charge dq from the opposite side of the ring, and when doing this, given that the charge is positive, the electric field vector will now point in this direction. Now comparing this to the previous electric field vector, which pointed in this direction, we can kind of quickly realize that the resulting final electric field, when we integrate over this ring, will only have a z component. So it will only have Ez pointing up straight away from the ring after we integrate over the entire ring. So when we do our integration, we don't have to worry about any electric field pointing perhaps along the plane of the ring itself. And this makes the problem significantly easier once we recognize this. So now we can jump into the mathematics. So electric field for a continuous charge is given by the equation 1 over 4 pi epsilon naught times the integral of the radial unit vector, so the unit vector pointing from dq to the point where we're evaluating our electric field, divided by the distance between these 2 points, and then integrated over all charge. Now, as we recognized, only Ez will be the non-zero component, so we can write Ez is equal to E, the total electric field due to the charge dq, times cosine theta. So this will give us the z component of this total electric field. And doing a little bit of trigonometry, we can recognize that cosine of theta is simply z divided by r. So we can write now our non-zero electric field. Ez is equal to 1 over 4 pi epsilon naught times the integral of 1 over r squared dq, and then times z divided by r. However, this integral over dq, the integrand within this integral, 1 over r squared, is constant. Essentially everywhere around this ring, no matter where we are, this vector r here is always a constant. So this is an integral over something that's constant. And if we can integrate over something that's constant, we can take that constant out of the integral. So we then simply have an integral over dq, and an integral over dq just gives us our total charge. And therefore we have our final answer. Ez is equal to 1 over 4 pi epsilon naught qz divided by r cubed. If we want to use Pythagorean theorem to write this r in terms of the radius of the ring and the height above the ring, this becomes 1 over 4 pi epsilon naught qz divided by capital R squared divided plus z squared, all raised to the 3/2 power. Now, a little bit more complicated, we can do a similar geometry, but instead this is a disk surface charge. So there is charge over the entire area of this blue disk here, and the charge density is given by sigma, and this would be in units of coulombs per meter squared. So we again start with our equation for a continuous charge. Electric field at our evaluation point is equal to 1 over 4 pi epsilon naught times the integral of r hat, the unit vector pointing from our dq charge to our electric field evaluation point, divided by the distance between these 2 points squared, and then integrated over all charge. So the method of integration for this problem will be your typical cylindrical integration. So we integrate in radius from 0 to the final major radius r, and we'll be integrating over some small dr prime at each r prime from 0 to the final radius r. We again, just like the last problem, recognize that the only non-zero component of our electric field will end up being Ez, and we again have a similar form of our integral with having this cosine of theta term. However, now this cosine of theta term is inside of our integral because theta changes over the course of the integration. So because r prime changes as we integrate out in radius, theta, which is going to be equal to z divided by r, changes as well. So if we write cosine of theta using trigonometry as z divided by r, we can write this integral as 1 over 4 pi epsilon naught, the integral of r hat, our unit vector, z divided by r cubed dq. However, we don't want to integrate over dq, we want to integrate over dr prime, as this is a cylindrical integration. dq, are the charge that we're integrating over at any given time, can be related to dr prime using the following relation. So dq is equal to the charge density times our differential area. The charge density is given here as sigma, and the differential area, essentially the area of this blue line, is going to be given by 2 pi r prime, the circumference of this blue circle, times dr prime, which is the width of this blue circle. Using this relation, we can then write the integral as 1 over 4 pi epsilon naught. The integral bounds from 0 to r, the final radius, 2 pi sigma big R prime z divided by small r cubed, and then integrating over radius dr prime. Now we need to change this small r to r prime so that we can perform this integral. R, which can be related to r prime and z using Pythagorean theorem, r prime squared plus z squared is equal to small r squared. R is also changing over the course of the integral, so we can instead write r cubed as r prime squared plus z squared all raised to the 3/2, and then we can take out some constants that we don't need to integrate over. So now this is the form of our integral, which gives us our non-zero EZ. I won't go over the proof as it goes a little bit beyond the topic here, but a integral of the form x divided by x squared plus c squared, where c is some constant, all raised to the 3/2, results in 1 over square root of x squared plus c squared plus some integration constant. Given this result and plugging in our appropriate bounds into this integral, we obtain the result that the electric field is equal to 2 pi sigma divided by 4 pi epsilon naught, all multiplied by 1 minus z divided by the square root of z squared plus big R squared. And that concludes lecture 2 of our Introduction to Electromagnetism series. We covered superposition and electric fields. In the next lecture, lecture 3, we'll be going over electric field lines and an introduction to Gauss's law. Thank you for watching No Fuss Physics. If you enjoyed the video, please give us a thumbs up. If you would like to follow this series or a different series, please subscribe. Thank you.